Okay, so we're going to start to look at magnetic fields. You may have been familiar with the magnetic fields you'll find around a normal magnet, like on the one shown here. There's a north pole end and a south pole end. And if you sprinkle iron filings, you can sort of see them showing that magnetic field shape around it, where they're very strong at the poles there, as shown. And there's a picture of one here. So by definition, you've actually got a north test pole that they consider. And so the field lines that are drawn show you the way that a north test pole will go. And you can see some examples here with the pair of bar magnets where the north is with the south, and there's two norths there. What we're interested in is the magnetic field around a single current carrying wire, because all current carrying wires will have a magnetic field associated with them because of the moving charges that go on in there. And you draw them as concentric circles around the actual current carrying wire. To work out which way they're going to be going, there's a right hand rule you can use, and I'll just show you that one first. So you can use the right hand rule to work out which way the magnetic field will be going around a current carrying wire, and you just put your thumb in the direction of the current, the I there, the intensity of current, and that's positive current, and the magnetic field B will wrap around in a circular pattern around the fingers there. You can see that in the photograph that's shown over here, just there. It's going from positive to negative there, and you can also see it over here in the cartoon version. Now there's another convention to be aware of here. If you think of an arrow with the feathers at the back there, so the arrow's got a pointy end there which actually represents a dot, and it's also got a back end here where you've got the feathers, which is normally indicated by a cross. So if you see a circle there with a cross on it, it actually means the current's going away from you, or the item's going away from you. And if you see a dot, it's the pointy end, it's coming towards you. So this one here is showing that the current is coming out of the page, as it says down the bottom. This one here's got a current going into the paper. So when you do that, if you imagine your thumb coming out of the page there, then your fingers will wrap around there in an anti-clockwise direction. Okay? Whereas if you point your thumb into the page here, you'll find your fingers are wrapping around in an anti-clockwise direction. You'll also notice here that the field lines are actually concentric. The circles have got a common centre there, and the field lines get further apart as you go out, which means the field's getting weaker. Now it's actually not an inverse square law, this one. If you go and check the magnetic field strength around a single wire there, it's proportional to 1 on D. And the reason for that is that it's not actually going out here in straight lines from a point source like this, where as you get twice as far away you get a quarter of the force or the field. Here you're going to get twice as far away, gives you a half of the field strength. Now this formula, the full formula for this, is B equals mu naught on 2 pi, which has got a constant value. It's 2 by 10 to the minus 7 actually, times by the current in the wire divided by the distance from the wire. Now that formula is not in this current course. Okay, all we're really interested in is, can you draw the field around a single current carrying wire where it's going into the board, the current, or coming out of the board, or in this case out of the page. And that's the rule we're using. It's called the right hand grip rule or the right hand curl rule. Okay, so that's the first thing you need to be able to draw. Can you draw one of those two here? So the second one you're supposed to be able to draw is around a coil, around a single coil of wire. So if you can imagine a coil of wire coming in like that with a current, what the field strength looks like around this sort of coil. So one of the ways of drawing this in cross section is to think of the coil as coming out of the board on one side, here, and coming around and going into the board or into the page. So if it's going into the page here and you put your thumb into the page, you're going to have a field that's going around there like that, going around clockwise. Okay, my apologies for the diagram here. Coming out of the page is going to be going this way around with your thumb like that, and something like this. Now what you'll notice here then is, as you get to the middle region in here, the field lines are going in the same direction here. They're going down the same direction. So we would expect the field in here to add together to be quite strong. Okay, so a way of drawing this, what's typical coil one, is you could draw it like this here. Okay, so this is rough, the curves aren't as smooth as I'd like them to be. You'll notice here that the field is slightly stronger on the inside here than it is on the outside, and you can tell that because it gets further apart out here. And in here they're pretty close together. So that's a picture you could use. Here's a couple that you can get off the internet though. So there's one with the lip turn on its side. So you'll notice here you're getting straight lines with a bit of curving as it comes out. And here the field is definitely weaker on the outside of the coil than it is on the inside, where the field is all going in the same direction. So they add together to give you a stronger one. Here's a picture of one where they've actually put a current through a coil of wire there, or this is actually multiple coils of wire in fact. And you can see that the magnetic field has actually changed the iron filings around that and started to follow that same typical shape there. Okay, so let's just have a look at a couple of those. I found this one by Peter Fletcher from the University of Southern Queensland, and he's going to try these three different sort of situations with magnetism that we're going to use. He's got some wires going into the page there, or into this piece of plastic. He's got a coil of wire, and he's got multiple coils of wire, which are the three that you need to know how to draw. So let's just have a look at those. Here it goes, turn the current on now. You can see the magnetic field's forming there. They've already started to form those rings around it, okay? Turn it on again, you should get the same sort of pattern. Turn it on again, and you should be able to see those rings forming. So now let's have a look at the coil of wire doing the same sort of stuff here. We turn that on. So that looks pretty good. You can see what's going on there. And if you freeze frame that for a second, you can see the lines sort of forming that typical relatively parallel through here, and then curving as it comes out, and curving as it comes out. And you'll find there's a stronger field inside the actual coil here than there is outside the coil, because these are not showing much lining up outside here. Feels quite weak out there, but it's obviously quite strong through here, and even the inside edge here compared to out here. So that should show you this idea of what happens if you do it as a coil of wire. So you can draw it like this, or you can draw it, this one's on the side there, and that's the way you're sort of getting it as a result. If you started to put another set of coils straight after this here, another set, so it was continuously looping as what's called a solenoid there, where you've got lots of coils tightly wound, you should find that this actually flattens out even more, and you get a very uniform field on the inside here. So let's just have a look at. So with the solenoid here, where you got it going the coil after coil after coil after coil, you'll find through the center the field becomes very uniform through there, and you get that curving at the end. So because the field lines are coming out away from here, that's like a north pole, because it's actually behaving like the north pole of a magnet. It's going to push north poles away. Here the field lines are coming in, which means north poles will be attracted. This is the south end of a magnet. So this is very much like an old magnet here that you would have done as a bar magnet. So the current's coming in over the top here. You can use your right hand rule to check that, the direction there. Obviously the field is weaker out here, and it's quite strong and uniform in the middle, and strong and starting to become non-uniform as it leaves that pole there. So there's a few ways you can draw it. There's one here as well, and that sort of thing could be shown like this. Ideally we want those wires to be more tightly bound to be a solenoid, but you get the idea there. The field in here is quite even there, quite uniform and quite strong, and you get some curving at the end here as it pulls away, but not much on the outside. Okay, and you can see this from this other picture. There is a formula for this you could use. The magnetic field inside the solenoid would be a constant times by the number of turns times by the current in the actual conductor itself. Okay, so they're the three you've got to be able to draw. Can I draw the field around a solenoid here? Okay, now if you're going to draw it with the out and in idea, in this one we've got it going into the board there, like that, and out on top. So you've kind of got multiples of those. So what you've got here is you've got the current going in at the bottom, coming out at the top, then going around, in at the bottom, coming around at the top, and it's going like that. It's looping around like it's shown in this diagram here. Okay, so the field then, if you check that, if this is coming out of the page here, you would have your right hand rule showing a curl that goes that way. So you've got to remember there's a field here that's actually going around this way here. So the field will come through the center in that direction, relatively uniform. Okay, through the center there. Hard to draw with this as it is at the moment. When it gets to the ends here, it will start to curve away. Okay, and the same at that end there. And you can see it'll form that sort of shape there. So uniform in the middle, non-uniform at the end of the poles there, and then it comes around and goes a lot weaker out here. But you get the picture better from this one here. But that's the way you may draw it if they actually give you dots and crosses into the board and out of the board. Out, in. Alright, thanks.